Okay, so I'm probably gonna go kind of quickly through these lessons. I just want to have a video record of them. I'm in a different classroom, just due to some limitations that I'm currently under. And I want to do ones where I'm up at the camera again, or up at the front of the room, but this will have to do for now. So we're looking at the integral of 1 over x in the form of 1 over, and the form of 1 over x, or 1 over u. So from earlier this year, we've talked about the derivative of natural log of x is 1 over x. So if we reverse that, the integral of 1 over x is going to be natural log of x plus c. And I'm kind of skipping talking about this absolute value. So I just want to remind you really quick, I'm going to draw a quick picture. If we look at the graph of the natural log of x, that graph looks like wee. If we compare that to 1 over x, we're going to see the graph of 1 over x looks like this. Now, they both have a vertical asymptote at x equals 0. But you'll notice that over here, things are different. Over here, 1 over x is defined, but over here, natural log of x is not defined. So kind of a short answer to why we throw these absolute value bars on here is because 1 over x is defined when x is negative, but natural log of x is not defined when x is negative. So a couple other things to remind you about natural log is natural log of x literally translates to log base e of x. And e is a number. E is not a variable. E doesn't change. It's approximately 2.717 or 718. So it's similar to pi in kind of its characteristics. It's this irrational number that goes on forever. So whenever we're seeing this, it's really a log with a base e. If you don't know what that means, so if we said log base e of x is equal to 5, this could be rewritten as e to the 5th power is equal to x. So x is whatever you get when you take e to the 5th power. So in this case, that's 2.717 blah, 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 to the 5th power, which is going to be some big number. And so x is going to be some big number. So if you ever see like ln of x is equal to 3, that would be saying e to the 3 is equal to x. And again, we can just calculate that and find it. So remember, the variable is now, I don't always write the words to these. We call these a dummy variable. As long as this and this match, it doesn't matter what it is. It could be a Q, it could be a W, it could be pick a different alphabet and use one of their letters. It doesn't matter. So if I want to take this integral, right off the bat, it's not 1 over t, it's 4 over t. So it's not identical. It's not just going to be the natural log of t and then plus c. Instead, what we need to do is remember that 4 over t is equivalent to 4 times 1 over t dt. So 4 over t is the same as 4 times 1 over t, which I could then, this is 4 times it. Since it's just a number times our function, I could pull the 4 outside of my integral and get 4 times the integral of 1 over t dt. And 1 over t I do know, so I can say it's 4 times the natural log. Wait, no, I'm supposed to do cursive natural log so that it's more easily distinguishable. Natural log of the absolute value of t plus c. So, great. Now we get into a slightly more complicated situation. This is not 1 over x dx. This is 1 over mes dx. So we're going to use u substitution here, where we say u is equal to 6x minus 1, which that on its own will let me say 1 over u, which is great, but I still have that dx, and we need to figure out how to get rid of the dx. So to find out what dx is, I'm going to differentiate here. I'm just going to remind you, the way we take the derivative of u, the first step is it says du dx is equal to, and then we take the derivative, so I get 6. and then I separate out my differentials. So this is divided by dx, so I'm going to multiply both sides by dx. Excuse me. Cancel. So I got du is equal to 6 dx. So if I go and look up here, I have a 1 over u, and then I have this dx. So I'm going to solve this and get dx alone. I'm going to divide both sides by 6. And so this is 1/6 du is equal to dx. So because of that, I can replace du with 1/6 du. Sorry, I can replace dx with 1/6 du. And as always, hop down in the comments and criticize me for misspeaking and stuff like that. It does help me. So at this stage, I would not personally write it like this. Just people have complained that putting this in here and not showing that, oh, this gets replaced with the 1/6 du, like they get mad about that. So multiplication is commutative. So I can, and this is this function times a number times du. So I can really say this is 1/6 times the integral of 1 over u du. Oh, well, 1 over u du, it's going to be 1/6 natural log of the absolute value of u plus c. It almost looks like it says luck, but it says lunuk. So 1/6 natural log absolute value. So we'll just drop, instead of u, we'll drop in 6x minus 1 and call it a day. Yay! All right, so I am trying to get through as much as possible today for those of you who weren't here. So we did all these in class. So this next one, so in class we had a nice conversation about this. They said, okay, this is the natural log of x, the 1 over x section. So we know that we're probably going to be doing that for like all the questions. But how do I know when to do it and when not to do it? And that's a really important question to ask. Like, so if we look at this first example, I'm just kind of writing it up here to give myself a little bit more room to discuss it. So which one should I pick for u? Well, okay, well, let me try 3x squared plus 1. Let me try that. So if I try that for u, and I say u is equal to 3x squared plus 1, the numerator, well, then I'll get du is equal to 6x dx. Okay. Well, maybe I need to like solve this for dx. So let me divide by 6x and get 1 over 6x du is, wait, now I've got x's and u's together. I'm not sure this is going to be the right way to handle this. Let me instead try making the denominator equal to u. So let me say u is equal to x cubed plus x. So du is equal to 3x squared plus 1 dx. And now what we see is a perfect match. We see u right here, and then we see 3x squared plus 1 times dx, which is that numerator. Remember, I can really think about this as 3x squared plus 1 times 1 over x cubed plus x dx. Like all the time, all of these, I can think about it as the numerator times 1 over the denominator. The numerator times 1 over the denominator. They're really two separate things. So for this first example here, because of this, I've got the 1 over u, and then I've got du, because 3x squared plus 1 and dx together is what du is equal to. And so in the end, we wind up with the natural log of the absolute value of u plus c, which is, well, u was equal to x cubed plus x. And this really is going to be our antiderivative. That's all that this turns out to be. If I take this derivative, I'm going to wind up with that. So let's keep going. So on this secant squared one, we can try the numerator. It doesn't work. We can try the denominator and say that that's u. If we say u is equal to tangent of x, well then du is going to be equal to the derivative of tangent x, which is secant squared dx. oh snap, secant squared dx. So we have another perfect 1 over u du substitution. So when we take that antiderivative, we get the natural log of the absolute value of u plus c. I almost skipped a step. So natural log of tangent x plus c. And if any of this is going too fast, you may want to go back and spend some more time on u substitution itself. And just drop me questions about that. Talk to me about it either on Schoology or in the comments. I think I have an issue with my phone getting notifications from YouTube, so if you want to be more reliable, do Schoology. I'm workshopping it though. Okay, so next question. Maybe we have another perfect one. Well, let's see. If I set u equal to the x squared plus 2x, then du is equal to 2x plus 2 dx. That does not fit here. I don't have x plus 1 dx here. So let's think about this. I've got my 1 over x squared plus 2x times my x plus 1 times my dx. I've got all that. So I have x plus 1 dx here. Is there anything I can do to this to make it say x plus 1 dx? And the answer is yes. I could divide both sides by 2. Or factor out of 2, then divide by 2. So I'm going to say 1/2 du is equal to x plus 1 dx. And so now, when we go in and we replace, we'll have our 1/2, which I can just immediately pull out front. If you don't know why I can immediately pull it out front, go and look at the steps from one of the previous problems where we pulled a fraction out front and see that those same steps will work exactly the same way. So the 1/2 will be out front, we'll have our 1 over u, and we'll have our du. And so it'll be 1/2 natural log of the absolute value of u plus c, which is 1/2 times the natural log of x squared plus 2x. I do not pause there for effect. I really forget what u equals. So I know I'm burning through these. I am trying to get through 3 lessons today, and I don't have a ton of time. So long division. All right. So this is a special tactic that is possible, improbable, but possible to see on the, I almost said SAT, on the AP exam. So if we have this situation, and I try setting u equal to x squared plus 1, then du is equal to 2x dx. That doesn't really match here. So maybe it's not like a natural log situation. Well, let's keep going. Let's try setting the numerator equal to it, and some of you may already realize that's not going to work. So when I take that derivative, 2x plus 1 plus 0, that's gone, dx. Well, g, that doesn't work either. So neither of those worked. One thing we could do is we could divide these out and see if it looks any cleaner. So I will use the technique known as long division. This is identical to the way that long division works, or not identical, analogous. It's very, very similar to the way that long division works with just plain numbers. So the first thing I ask myself is, okay, how many times does x squared go into x squared? Well, it goes in 1 time, so I can put a 1 up here, x squared, and then I multiply that 1 times x squared plus 1, and I get x squared. There's nothing here, so I'm going to leave it blank, and plus 1. And then when we subtract them, cancel, 1 minus 1 cancels, x minus nothing is x. So I wind up having an x. So I'm not going to say 1 remainder x, although that's true, my remainder was x. It was remainder x when my denominator was x squared plus 1. So the way that I can write this is 1 plus x over my denominator. And you may be wondering, why turn this into this? This is not quite as ugly as this is. This is uglier, but just bear with me. If we rewrite this, this is two things added together, which when we're doing integrals, we can think about them separately. I can really think about the integral of 1 dx. I'll leave the 1 in there just in case that bothers you, I'm leaving it out. And then I can think about this integral on its own. So the integral of 1 is so easy you might not realize what it is. What did I take the derivative of to get 1? I took the derivative of x to get 1, so this is just x. Now this one, I got to do a little bit of u subs. So I'm going to put a little box here, and we'll just hop over here for a second. So integral of x over x squared plus 1 dx. So if I set u equal to the denominator, x squared plus 1, because it's the more complicated thing, let's see, du is equal to 2x dx. That's close. I just wanted to say x dx though, because that's all I have left. So I'm going to divide both sides by 2 and say 1/2 du is equal to x dx. So now I can rewrite this as 1/2 1 over u du. So now I can write plus 1/2 natural log the absolute value of u plus c. And we'll just finish it up by resubbing in our u value. So x plus 1/2 natural log absolute value of x squared plus 1 plus c. We could look at examples like this for hours and hours and hours and see a different strategy and a different technique every time. There's a limited number of techniques that the AP exam is going to use. They're not going to expect that you know literally everything. Literally everything there is to know about u substitution in calculus. So this is one that may pop up. So here's another one that may pop up. And that is our dreaded double u substitution. So remember, in double u substitution, the idea was that you perform your u substitution and there's not enough to just finish dropping everything in with u and du. And there winds up being a little bit more that we have to do. So experience has taught me that I'm not actually going to use the entire denominator, the x plus 1 squared. I'm just going to use x plus 1. So that's experience that taught me that. I would, earlier on in my career, I probably would have tried x plus 1 squared and try that first and find out that that's not very helpful. But having done this for a number of years, this one tells me, my brain tells me that this is going to be a wiser maneuver, even though du equals dx doesn't get rid of this 2x up here. Right now, all we're really able to get rid of is, we got a u squared down here. I'm still stuck with a 2x and a du over here. And the silly phrase that I like to use to remind everybody here is that u and your x shouldn't be together anymore. So I should never have you and your x in the same place at the same time. I'm not trying to give you life advice with that. How you deal with your x's in real life is completely up to you. And as a math teacher, I don't have any room to speak on that, but hopefully that is a helpful reminder that these two should never be in the same room together. So because of that, we want to figure out a way to eliminate this 2x and have it say something different. And that's where our first little substitution equation came into play. If I take u is equal to x plus 1 and I were to solve this for x, then I'd be able to write something else here. So let's try that. U minus 1 is equal to x. Oh, snap. So over here, instead of writing 2x, I can write 2 times u minus 1. And down here, I've got my u squared. I've got my du. And if I were you, but Mr. Canfield, this is not any better than this, just we've replaced x's with u's and it's still just a big mess. But that's where we're wrong. Remember, a plus sign in the denominator, there's nothing I can do about it. But a plus sign in the well, I guess it's a subtraction, but plus and minus work very similarly. A minus sign in the numerator is a really good thing. I can actually split this into separate fractions now. So remember, we'll distribute the 2, or you can take it out front. I'm distributing it for, I think it's going to be clearer to more people. So if I distribute this, I can now treat this as the integral of 2u over u squared du minus the integral of 2 over u squared du. And now we have these two separate integral, yeah, I did that right. So these two separate integrals to work on. So we'll do the first one first. So it says 2u over u squared. Well, u over u squared is going to simplify to 2 over u, because there's a u and there's a uu, right? This is 2u over uu. So one pair of those u's will cancel. And I can do that integral from earlier. It's going to wind up being 2 natural log of the absolute value of u plus c, but we'll just tack the plus c on the very end. And this one, 2 over u squared. Recall with me, this is 2u to the negative 2. So I'm going to add 1 to the exponent. And then divide by my new exponent. Plus c. So before I resub in x's, that's a double negative, so it's going to be plus 2u to the negative 1 plus c. And I shouldn't leave it like that. I should rewrite this as 2 over u. So 2 natural log absolute value of u plus 2 over u plus c. So now we've got 2 natural log, I'm going to plug x's back in, plus 2 over x's back in plus c. And u was equal to x plus 1. So, horrific mess, but possible. So this, impossible with our current strategies, but with a little manipulation and that double u substitution, we can break it up into 2 separate integrals. All right, time for trig. To keep this lesson shorter, I'm going to say you need to just look up what these are and memorize them. I derived tangent in class, and I'd be happy to work with you if you're interested how the rest of these work. It's more of a timing issue, because even though I'm videotaping this and I have all the time in the world, I still have time constraints right now. If enough of you complain, I'll show you the rest of them in a future video. Okay, there's a list on the next page, and it's really, really helpful. So first thing we want whenever we're doing trig, and I said trig, and I meant to say integration. So whenever we're doing an integral, look and see if it's a basic form. Is it like something to a power, or is it a natural log, or is it trigonometry, or is it e to the x? Is there something where it's like, in general, this always integrates like this? If it's that, we may need to use u subs using one of those ideas. And this is a big one. Trial and error a lot of times is what we have to do with a u, until you've found enough of them that you can kind of intuit your way to it. So don't feel bad if you ever get a u incorrect. It just means that it's not that one, and we can try something else. So I really liked this. If you can't figure it out with u substitution, try altering what's in the integral. Try maybe a trig identity, multiplication and division somehow, like by the same thing, turning things into fractions, or then adding and subtracting something. Or these are, you know, advanced tactics, and then get creative. That really is in the book that I copied this from. It's not always like a clean answer, because remember, these weren't things that humans were like, oh, well, let's decide that the answer to this integral is this. They were like, oh, let's try to integrate this. Well, how are we going to get the answer? And then they figured out what the answer was. So it's not always like a puzzle that somebody devised for you. It's something that exists that we're trying to figure out. So, and then your calculator, if you don't already know how to do this in your calculator, I can show you how to do that. no matter what kind of calculator you have, it's going to have an integral function on it. TI 83, 84, 89, they all have integral properties. All right. So here's a good chance to apply the guidelines. I'm doing this one blind. It's been 2 years since I've done this problem, so I don't remember what it is. So let's start out. My first guess is I'm going to use u substitution, and I'm going to set u equal to 1 plus tangent squared x. So that makes du equal to 0 plus 2 tangent x times, remember that'd be the 2 out front, to do chain rule on this. I'm already regretting this decision to do u subs here. Secant squared x. Okay, so dx. I don't see any of this in here. This tells me that maybe this wasn't the right approach. Let's try something different. Let's try altering the 1 plus tangent squared. Let's see. Well, I know that sine squared plus cosine squared is equal to 1. Okay. That doesn't say that. It says 1 plus tangent squared. So in order to make tangent appear here, tangent squared, I know tangent is sine over cosine, so I'm going to divide all these by cosine squared. Now I'm going to find that sine squared over cosine squared is tangent squared. Cosine squared over, oh, that's 1. And then that's going to be secant squared. Well, hey, that's pretty fantastic. So instead of writing 1 plus tangent squared here, I could write the integral from 0 to pi over 4 of the square root of secant squared x dx. And you may be thinking, Mr. Campbell, that looks awful too. Well, yeah, but we're taking the square root of something squared. I can simplify that further to the integral of secant of x dx. And now all I have to do is that formula that I totally remember, and I'm not going to go look up right now.